Dear all, welcome back to the very basics of data structures and algorithm. And in today's session, we'll be studying the master theorem. So without wasting, let's start. First, we'll be understanding that what master theorem is. Master theorem is one of the most fundamental and most used theorem that we will be using. We mostly use this theorem in case of recursion or a recursion type of problem where we get a lot of solutions, lot of problems, but master theorem helps us to find the solution very quickly. That means if you are preparing for placements or you are giving some competitive examination and you have a large code diagram and you want to execute in just minutes, then you require the master theorem. So without wasting time, let's look it. Master theorem is a special case of theorem that we can apply in this type of form. If the form is of that type, then we can apply master theorem. That means that have to satisfy this form. So mostly we'll be comparing with that type of form. A t n by b plus theta of not nk, this is theta of n to the power k log n to the power p. So if the form matches with this equation, then we will directly implement this formula. So this is the form that we will be checking for, form of equation that we will be checking for. And if we try to understand by theoretically that what this value is, in our equation A will be nothing but a coefficient, but in terms of understanding, A is number of subproblems, B, this B is factor by which problem size is divided. Here the problem size means recursion problem size because the recursion problem keeps growing. F of n, this is the portion f of n that is work done outside recursion or merging process. So that is about master theorem. Now we will be understanding this formula into deep dive. The at n by b plus theta of n to the power k log n to the power p. So this is the main form that we will be comparing for master theorem is that t of n, we will be comparing t of n that is equals to at n by b plus theta of n to the power k log n to the power p. So here you note a, b, k, these are the factors, and depending upon the values of a and b to the power k, depending upon the value, by comparing the value of a and b to the power k, we will be having three type of solution. This is just a large algorithm and we want to solve just by memorization. So based on the conditions, there are further divided formula. So the conditions based on those comparison, what that can be either when a is greater than b to the power k. That means a condition that can be number one condition, a greater than b to the power k. Second condition that can be a is b to the power k, a equals to b to the power k. The third condition that can be from here is that a less than b to the power k. So that will be the third condition, a less than b to the power k. So we have got the conditions that a greater than b to the power k, a equals to b to the power k, a less than b to the power k. So after once we have gotten that type of combination, here also we divide the formula into based upon three more conditions, and the condition is the value of this p. The condition is the value of this p. We will be comparing here if the value of p is greater than minus 1, or the value of p is equals to minus 1, or the value of p is less than equals to minus 1. Here we will be comparing with the value of minus 1. Now notice this condition, the third condition. Here also we divide, or we have the formula, okay, and in the third case we also divide the third case, but comparing the value of p, but not with 1 but with respect to 0. So here also we compare, but with respect to 0 is the case. So here we will be checking if the value of p is greater than equals to 0 or the value of p is less than 0. So we will be checking all those three conditions, and based upon those conditions we will be having formula. So let's look the first one, a greater than b to the power k. When the condition is that our value of a is greater than b to the power k, so this is the case 1. We can this is our first case where we are getting a b greater than b to the power k. Then if our equation suits with our algorithm, then we'll be utilizing the formula of t of n, that is equals to theta of n to the power log a base b. T of n, that is equals to theta of n to the power log a base b. Okay, so that is the formula that we will be utilizing here. Theta, that defines the exact value. That means we will be getting the running time or time complexity for whatever the case we apply this formula, we will be getting the answer directly. So here we can call it the time complexity. So that will be the exact time complexity. So if the condition satisfies first one, now we are dealing with the second condition. If the condition satisfies the second one, so there will be three conditions. Further we will be checking if the value in our equation, look this equation, there will be p, let's say it can be like n square. If this is n square, that means log of n is whole to the power 0. Just imagine, only when the p will be equals to 0, it will be 1, and we will be getting equals to n square. That means here we get p equals to 0. So this way we will be checking the value of p here, and based upon the value of p, there will be three formulas. So first condition, when p will be greater than equals to -1. Now we are elaborating these conditions. If p is greater than equals to -1, when p is now we are in the case 2. Now we are considering about the case 2, when a equals to b to the power k. Now case inside this, if p is greater than -1, if this satisfied, then our formula will be log n to the power p plus 1. This is multiplied with this n, this is, so these are two different portions, and then that will be the time complexity if p is greater than -1. So that is the case 1. Now if second case, if it satisfied the second case, that is if p equals to -1, then the time complexity will be theta of n to the power log a base b into log of log n. So if p is -1, it is satisfying the second condition of the second, I mean we are inside the second, then t of n, that will be theta of n to the power log a base b into log of log n. So that will be the formula, that theta of n to the power log a base b, we have written it log a base b into log of log n. So this is the condition when p equals to -1. Now the formula when this is satisfied, that is p is less than -1. So inside the case 2, if p is less than -1, then t of n will be equals to theta of n to the power log a base b. Then t of n will be theta of n to the power log a base b. So one thing you can notice that in our second case, this position theta of n to the power log base b, theta of n to the power log a base b, this is a fixed and common portion, and you get if p is greater than -1, then log n to the power 1 plus p is multiplied with it. Here when p equals to -1, log of log n is multiplied with it, and when in p is less than 1, only 1 is multiplied with it. That means this value is becoming 1. So this is a helpful portion that we can easily correlate those equations. Now this is the case 2. Now when the value will be less than a to the power b to the power k, that is a case 3. Case 2. Now considering the case 3. Case 3, that is a less than b to the power k. A less than b to the power k. When a is less than b to the power k, we again consider the cases of p, but not with respect to 1 but with respect to 0. So we will be checking one condition when p will be greater than equals to 0, when p will be less than 0. So if p is greater than 0, if this condition is satisfied, then the value will be theta of n to the power k log n to the power p. Then the time complexity exact will be theta of n to the power k log n to the power p. Okay, and if p is less than 0, then the time complexity will be t of n, that is equals to theta of n to the power k, theta of n to the power k. So these are all the equations that you got based on the three conditions. First, what we check, first master theorem, we check if our formula matches with this master's standard form. So this is a standard form. We'll be checking if our equation, recursion equation, matches with this standard form, that is the standard form, matches with our standard form. If it's matched with our standard form, then we'll be checking the conditions of if the value a and b, the value b to the power k, these are equal. If those are equal, then we'll be coming into three cases. The three cases is, number one cases when a is greater than b to the power k, number one case. Number two case when a equals to b to the power k, this is the second case. And number three case when a is less than b to the power k. So these are the three cases, and depending on the three cases, again we compare with the value of p. If p is greater than -1, p is equals to -1, p is less than -1. If p is greater than -1, then our exact time complexity t of n, that is theta of n to the power log a base b into log n to the power 1 plus p. This in log a base b, this portion is fixed for everyone. If p equals to -1, then also n to the power log a base b into log of log n, and if p is less than -1, then theta t of n equals to theta of n to the power log a base b. So this was a case 2, and in case 3 we again check the value of a and b to the power k, but with respect to, first we check if a is less than b to the power k, and if it's satisfied in case 3, then we check the value of p with respect to 0. With respect to 0, if that is greater than 0, then t of n equals to theta of n to the power k log n to the power p, and if that is less than 0, then t of n, that is equals to theta of n to the power k. So these were the cases of master's theorem. Now let's go deep diver into the cases, what it tells. This was the three cases of f1. Case 1 that I already discussed, that is if a is greater than b to the power k. If a is greater than b to the power k, then t of n equals to t of n, that is equals to theta of n to the power log a base b. The condition, the first condition one. Notice here in our this standard equation, a must be greater than equals to 1, b must be greater than 1, k should be greater than equals to 0, the value of this k should be greater than equals to 0, and p should be a real number, and this p, the p you are noticing here, that should be a real number. That is case 1. Now the case 2. We discussed in our case 2 that in our case 2 there will be three conditions based on the value of p. So the conditions, a must be greater than equals to 1, b will be greater than 1, k will be greater than equals to 0, and p a real number. That I have already told the conditions of standard formula. Now case 2, when a equals to b to the power k, then we check with respect to the value of p equals to greater than -1, if p equals to -1, if p less than -1, and the formula written here, that is n to the power log a base b, the common factor, into log n to the power p plus 1. If p is equals to -1, then t of n, that is equals to theta of n to the power log a base b, the common portion, into log of log n. If p less than -1, then also t of n, that is equals to theta of n to the power log a base b. So this is the second condition, and now we will be discussing the third condition, when a is less than b to the power k. Then we check with respect to the value of p. If the value of p is greater than equals to 0, then t of n equals to theta of n to the power k into log n to the power p, and if p less than 0, then t of n, that is equals to theta of n to the power k. Now applications in our SD interviews, that where we utilize this master's theorem. We utilize this master's theorem in merge sort and quick sort analysis. If you have already studied the data structure algorithm, and if not, then you will be studying a lot of sorting algorithms. Among them, the most popular are some merge sort, quick sort, etc. Binary search, you will be studying. This is one of the most important topic. In binary search also we can utilize the master's theorem. Matrix multiplication search, in matrix multiplication search also we can utilize the master's theorem. Various algorithm optimizations like FFT, Stations, Carrot Suba, in those places also we can apply those algorithms. we can use in dynamic programming and divide and conquer optimizations also. And so in today's session we actually knew the applications of master theorem, where you can use the master theorem, also the real life use cases. These are the real life use cases. We will be observing all the real life use cases in next sessions, and for now we will be studying the master theorem and all those conditions, total 6 conditions, I mean main 3 conditions, then 3 to 3. So without wasting time, let's start the sessions with master theorem.